Hi everyone, we will now talk about another very important basic components in the power system analysis. That is the transformers and the synchronous machines, and with a special emphasis on the synchronous generator, of course. This is the chapter 3 in the book. In this chapter we first discuss the modeling of transformers and see the great advantage of this per unit calculations as we started on in the previous chapter. We also consider the transformers that regulate voltage magnitude and phase shifting. And in this and a later chapter we shall see how these regulating transformers are used to control the flow of real and reactive power, especially in the power and load flow lectures. Then the general equations developed for the flux linkers of the various windings applicable to both steady state and transit analysis will be described here now. So here you can overview of the sub-chapters in this chapter 3. So mainly the sub-chapter 3.1, 3.2 will be going through now in this lecture. And you can see there are some self-reading you need to do also. Then we have 3.4, the per unit impedance, single phase, and 3.5, three-phase transformers. Then we will look a little bit on the 3.7, three-phase transformers, phase shift, equivalent circuit, tap changing, and regulating. And then we will go over to the synchronous machine with the focus on the generator. So we will go through all of these sub-chapters of that part. Important part in both transformer and generator is of course that it has a magnetization curve of materials. The materials are magnetic. So here is a very famous this BH curve or saturation curve, and it shows like that the flux density is not linear with respect to the field intensity. So down we have the on the x-axis we have the flux density, and on the y-axis up here we have the magnetic flux density, the symbol of B, and it is in Tesla or in Weber per meter square. In the same way as the electrical circuit, we also have for magnetic circuit the so-called Ohm law for magnetic circuit, as you can see down here. And since magnetic electric circuits have similar characteristics, then we can apply the traditional circuit laws to magnetic circuits and so on. So here you can see the relationship between the B and the H, as I just said. Here you can typically see this magnetization curve, where it follows different paths depending on that it's excited or de-excited. Now the voltage is the MMF, the F symbol here, and the current is the Weber, the flux here, and of course R is the reluctance, the ohmic value in electrical circuit. So the Faraday's law of induction is one very important basic law related to the coil here. It's a basic law, as I said, of electromagnetism, predicting how then a magnetic field will interact with an electrical circuit to produce an electromotive force, the EMF, the small e here. So it's a phenomenon known as the electromagnetic induction, and it can equals the number of windings and also the derivative of the flux here. So it's flux passing through the specific coils. And it has also a minus here, you note the Lenz law. So it has like an opposite force it's producing when it is passing through the flux of the coil. And the flux can also be represented by the B times A, the magnetic field, the B in Tesla, and area. So it's the area of flux path. As you can see, of course, the number of windings is important, so a large number gives then a higher voltage. And from this we can see that if you want to have a higher voltage or induced EMF, you need to increase the number of windings. You can or you can increase the B field or the area, or you can also of course increase the speed of the derivative, like how fast it spins. You can spin faster, and this becomes of course important in the generator side. In the figure below here we have a typical radial, where you have the power produced in one side and it's transported to the load side. And typically voltage for production of power is for generators 11 to 30 kV. Then you have a step-up transformer, and you have then stepping up the voltage to, for example, 420 kV in Norway, 132, and then you are lowering then the voltage again, coming down to regional transmission lines, and then you can also even further lower it down to low voltage side with a typical step-down transformer. And in a step-down transformer, we can say that on the primary side, we can have many windings, high voltage and low current. And on the secondary side, we will typically have few windings, low voltage and high current. As we remember that in a transformer, the total amount of apparent power will be conserved or be the same. We have different types of transformer. This is typically what we call our power transformers. And then we have distribution transformers. So when it comes to types of transformers in this course, typically we can look at this power transformer and distribution transformer as already mentioned. So the power transformer are used in transmission network on high voltages for step-up and step-down application. And you can see here overall voltage levels that it can be typically used. And it's generally rated about 200 MVA. So it's used for transmission purposes, a heavy load, that's important. And it's also having a big in size typically, and compared to the distribution transformer. And in use in generating station and transmission substation and so on. So for the how it's designed, it's of course important how they're going to use it. So power transformers that are used in transmission network, they are not like directly connected to the consumers, so load fluctuation are very less than compared to distribution transformer. So that means that these are loaded fully during 24 hours a day. So such as copper losses, iron losses take place, takes very constant throughout the day then. So the average loads are nearer to the full load, you can see, or full load, and these are designed in such a way that the maximum efficiency is at typical full load condition. So and these are independent of time, of course. So in calculating the efficiency, only power basis is enough then. On the other hand, we have distribution transformer, and it's typically used then for low voltage distribution network, as it means to end user connectivity, and are generally rated less than 200 MVA, or much less actually. So it's used for as low voltage as I said, and it have a low efficiency, typically 50 to 70% maybe, small size, easy installation, and it has of course low magnetic losses can be. And it's not always fully loaded either. Here down you can see like inside of one of those distribution transformer have its designed. And we typically have then of course the low voltage bushing and the high voltage bushing. And we have an oil tank, cooling tubes. And then we have the laminated core, that's important for, as you can see here. This is one type then. So here is an overview of power transformers in Norway, and you can see the column for voltages. And so in Norway we have the highest 420 kV, and then we have 300 to 220 kV typically, 132 and 110 to 33 kV. And you can see the numbers and then the fault per 100 years. So of course at lower voltages, the higher number of installed power transformers we have. Quite amount on the 110 to 33 kV. Now let's talk about the ideal transformer. So transformer consists of mainly two or more coils placed, so they are linked by the same magnetic flux. In a power transformer, the coils are placed on an iron core in order to confine the flux so that almost all of the flux linking any one coil links to the others. So the flux linkage is important now further in the lecture. The feature you can see here, it shows two windings that may be placed on an iron core to form a single phase transformer, or so-called shell type. The number of turns in a winding may range from several hundreds up to several thousand.
When we talk about the ideal transformer, is three important aspects that you need to know about. The probability of the core, infinite. We talked about that a little bit earlier, but here is infinite. 2. All of the flux is confined to the core and therefore links all of the turns of both windings. And thirdly, the core losses and winding resistances are 0. So two things are important then is that the voltages E1 and E2 must equal the terminal voltages by this definition V1 and V2. And secondly, the instant voltage E1 and E2 are in phase when it's defined by the plus and minus polarity as indicated. Usually we do not know the direction in which the coils of a transformer are wound. One way to get winding information is to place a dot at the end of each winding, as you can see in the figure, such that all dot ends of windings are positive at the same time. That is, the voltage drops from dotted to unmarked terminals of all windings are in phase. Now continue to talk about the ideal transformer, now in phase form. So if you're using this dotted convention, as we call it, dotted here, we can make sure it's in phase. So as is written here, note that I1 and I2 current are in phase if we choose the current to be positive when entering the dotted terminals of one winding and leaving the dotted terminal of the other. So that's important. Another very important in such a schematic two-winding transformer is that we can have this law where we have the windings at the primary and current is equal the winding and current on the secondary. We can write it in this fashion, equals 0, or in this fashion. And here we can see that the primary current will be equal then the winding of secondary side divided on primary, multiply with the current on the secondary. So if the secondary current is 0, the primary current is 0. In the phase form we can have several relationships in some so simple schematic diagram. We can have the relationship between V1 and V2 should be equal then the E1 divided on E2, and should be equal the ratio turn N1 divided on N2. And we define that as the ratio when we use in our equations. We can then from this relationship again solve it from by V2, for example, and we can have N2 divided on N1 times V1. And then we can represent V2 equal to V1 divided on the A ratio. So if you want to have the impedance on the secondary side, we of course can use this relationship coming from here into here, and then we can also use the Ampere law as already stated, and we can just solve it regarding the I2 current, and we insert it here. Then we have this equation for set 2 where the impedance at the secondary side is now represented by a relationship between voltage and current on the primary side. That's a very simplification then will lead then to that the set 2 now the impedance connected to the secondary side is referred to the primary side, and it is then we will get then the ratio in square times the impedance at the secondary side. So this is how we can refer it to the other side, and this is a typical way we use it both in the transformer and the generator fashion. Also for the power we can have some important things that we can look at. In it, of course, we know that the complex power is the voltage times the current complex conjugate. So we can write down the relationship between on the primary side and the secondary side, and we can see that it becomes equal. So it's in such an ideal transformer we have a conservation of the energy. So the power on the primary side is equal to the secondary side. You can also write it in this fashion where the S rated is equal to the V1 and current rated, and then of course the magnitude of those is equal to the magnitude on the secondary side. You could also write it as current is equal then to the S divided by the voltage in conjugated form. And then we can have actually another expression for the impedance on the secondary side, representing then the voltage is squared, the secondary side, and of course the the apparent power, complex conjugated. We are now talking about the shell type transformer. Now we'll just go to what we call the core type of construction. So, but still, we continue to neglect the losses in the iron core. But the other three physical characteristics of the practical transformer are now more considered. Two important concepts is, of course, this mutually and self coils. So now we also in the feature, if you can see in feature A here now, we have defined the current into due to the right hand rule to get the flux in the same direction flowing. So the feature A is showing then the mutual flux due to currents current I1 and I2. So in B and C we are looking at each side separately. And if you look at the B side, we have a flux circulating here, what we call leakage. It's a leakage of flux, not producing the main flux, but it's a leakage. And this is the mutual flux, Phi21. So, and on the same side, we have the C, feature C here. We have also a leakage flux and a mutual flux due to the current I2 alone. And in the same current I1 acting alone on this here. So when we now talk about the flux linkage of coil 1 due to current I1 acting alone, this expression is given. So now we can see several different expressions below here, just to represent the self and mutual and so on. So for this here, the 1,1, there the N1 is the number of turns, as you can see, and L1 is the self inductance. And if you look at this 2,2 here, it has self inductance on the secondary side. And here is for the mutual values, also here for mutual values. Then you actually insert those relationship into relationship as you see here to sum it up, both for the primary side and the secondary side. Then we have included both the self and the mutual part of both acting on current 1 and current 2. So now both the current I1 and I2 are here, and I1 and I2 here. Now when the flux linkage change with time, the voltage drop across the coils in direction of the circulating currents can be expressed in the way you see here. Now I only show for the V2 part, where you have the resistance times the current and the derivative. Now we are inserted this expression here, and you can divide it like this, as you see here. And the positive sign of this equation here and are usually associated with a coil absorbing power from a source, as if the coil were a load. That is important for this here. So, but of course, if you look at below here, we have take the negative sign. So then we have the voltage drop across coil 2 is now reversed. So for positive instant values of V2 and I curve, power is being supplied by the coil. That's important. So positive supplied by the coil. Then for the negative sign, then the characteristic is a coil that's acting actually as a generator, delivering power and energy over time to an external load. So we often use an equivalent circuit to represent the practical transformer, and of course there are done some simplifications, and typically it does not reflect include any transformation special, and also does not include the electrical isolation of the primary from the secondary. And it does not include coil losses at all. But here you can see equivalent circuit. We will simplify it even more, as you can see from here. And if you apply a sine voltage with the secondary side open, we will have a small excitation current. And mostly we go to the magnetization part, here represented by the B, but you have so ohmic losses here. And when we talk about the losses. We typically have core losses that can be hysteresis losses, cyclic changes of direction of the flux in the iron. And we can also have these circulating currents that are induced, the eddy current, the ohmic losses in the system. It's worth to notice that the current in this B is much larger in the conductance here. This is susceptance. And as you can see here also, now we have the X2R2 from the secondary put on the primary side with the ratio square, as we talked about earlier. So in the idle transformer, this position is not fixed, as we say. We could make it to the left past the series elements. Then we just need to keep in track with the ratio changes. So often we are neglecting the exciting current because it's too small compared to the usual load currents in the system. So we can actually simply the equivalent circuit even further, as you can see down here. So now we have the V1 here and the ratio times the V2 here. And the R1 and X1 now, it can be represented as you can see here. So now the secondary is transferred to the primary side, and we become a really simple system. So the R1 is now R1 small plus the ratio and square times R2, and in the same manner for the inductance part. So here it also is summed up that all impedances and voltages in the part of the circuit connected to the secondary terminals must now be referred through the primary side. When it comes to voltage regulation, it's a definition. It's defined as the difference between the voltage magnitude at the load terminals of the transformer at full load and at no load, in percent of full load voltage with input voltage held constant. It can be shown then in this equation here. So the V2 no load is the magnitude of low voltage V2 at no load, and V2 full load is the magnitude of V2 at full load with V1 constant. So this is a way we can use when we want to calculate the percent regulation. Now we will come back to the per unit impedance calculation. So the ohmic values of resistance and leakage reactance of transformer depend on whether they are measured on the high or low voltage side of the transformer. We'll come with an example soon. If they are expressed in per unit, the base kilovolt amperes is understood to be kilovolt ampere rating of the transformer. So you need to locate that rating value. The base voltage is understood to be the voltage rating of the low voltage winding if the ohmic values of resistance and leakage reactance are referred to the low voltage side of the transformer. Likewise, the base voltage is taken to be the voltage rating of the high voltage winding if the ohmic values are referred to the high voltage side. So always keep track on which side you are referring to. Here's an example of one transformer from Siemens, and it's located a transformer at a generator called Åbjøra. So it's a three-phase transformer, and on the high voltage, høyspenning, it's 142 kV, and the low voltage is 11 kV. It's a delta connection here and a Y connection. We can also see that it has a U set here, referred to the 103 MVA on 12.9%, and also our ohmic value is given per phase on 25.2. So this is a sign is marked on that transformer. For the per unit impedance of the transformer, it's the same regardless of whether it is determined from ohmic values referred to the high voltage or low voltage side of transformers. So you can see in this case here, as I said, the Åbjøra, it was 103 MVA, 12.9% of impedance, and then it's a voltage V1 and V2 side. So the ratio is then, as we know, is the 142 divided on 11, 12.9, as you can see here.
So the impedance on the high voltage side can be calculated based on the voltage squared divided on the apparent power, and of course the amount of per unit value of the impedance. And then you will get the value on the high voltage side for impedance. The same you can do on the low voltage side. And we will have that the ohmic value, you see, will be, of course, be different depending on which side you are referred to. However, it's the same per unit impedance value that I used. You can also calculate a base value. Here's an example for high voltage side. As we learned earlier, this will be the base value on high voltage side. And then we will have can calculate then a per unit impedance value from the 25.2, as you find here, divided on the base. And we come then back to the same value as you have here. Now you can please go to the example 3.7 on your own.